And we discovered that it wasn't 88 days. It was only 59 days. Mercury doesn't keep the same face all the time, but it turns 1.5 times every time it goes around the sun. And because it's so close to the sun, you can really only observe it every other time. And so, like seeing the spokes in a wagon wheel on the movie screen that appear to be standing still, it was a stroboscopic effect because of the coincidence of the Earth's orbit, Mercury's orbit, and the spin of Mercury. He kept seeing Mercury in the same position and came to the logical but wrong conclusion. In fact, Mercury spins 1.5 times for every Mercury orbit. Almost correct. But the ability to observe Mercury that carefully was tremendous. And he made the conclusion that seemed logical at the time and was necessary for us to go on, and when we discovered it was wrong, to come into a deeper insight of how Mercury actually moves. Next thing he discovered, the thing he's most famous for, with his keen eyesight, with a brilliant telescope for the 19th century, he carefully looked at Mars. And he looked at Mars with telescopes all along. Most people before him looked at Mars to calculate the position of Mars. And how does its orbit move? He looked at Mars and asked a brand new question. Not where was Mars, but what was Mars? And by looking carefully, he mapped out a series of dark areas and bright areas on the surface of Mars, gave them names, the names we use even to this day, just as the early maps of the moon were named by a Jesuit priest, Riccioli, whose book, Cosgrani, is wonderfully translated recently, and named the same names we use today. Schiaparelli's names we still use today. But every now and then, looking through a telescope, the air, which normally is shimmering so that looking at the sky is like trying to look at the sun from the bottom of a swimming pool with the water above you swirling back and forth. Every now and then you get a momentary burst of stillness, and he could swear he could see thin lines on the surface of Mars. And once he reported these using the Italian word canali, which Percival Lowell mistranslates as canals, other observers looking at Mars sees those lines in exactly the same place. And he gave birth to 100 years of wonderfully bad science fiction about Martians building canals. The modern astronomers don't see these. The spacecraft don't see these. We do see the dark features. We do see the light and dark regions, but we don't see the canals. What we do see is that if you take an image of Mars and put it into Photoshop and twist the knob that says unsharp masking, you can recreate the optical illusion of dark regions and bright regions so that your eye seems to think there's a line connecting them. A brilliant piece of observation, mostly correct until he went a step too far. My favorite sad story of Schiaparelli was he was fascinated by showers of meteors, shooting stars. Every now and then you'll see a shooting star in the sky, but you know there are certain nights when year after year the tears of St. Lawrence, the Perseid shower, will occur like in the middle of October, or in the middle of August, rather. Or the Leonid shower, which occurs in November, I hope. Yeah, good. It's either November or October, I remember. What he was able to do, Schiaparelli, was to recognize at a certain point in the year, that means when the Earth is a certain point in space going around the sun, it encounters a shower of meteors, which means the Earth is plowing through a cloud of dust. And this cloud of dust, in the case of the Leonid shower, gets super bright every 33 years. So he can work out the direction of where the dust is and the 33-year period and calculate that this dust is also going around the sun with a 33-year period with a certain shape and position of orbit. And you know what? There's a comet with exactly the same orbit and period. Comet Templeton. And he recognized for the first time that meteor showers and comets were related to each other. No one had ever done this before. We can now identify every known meteor shower, every periodic shower, with a given comet. Brilliant work. What makes this almost correct? After he sees that there's a connection between comets and meteor showers, which I think you could probably figure out is because the dust be pouring off the back of the comet. To him, no, it was not the dust pouring off the back of the comet. He says, obviously, gravity doesn't cause things to fly apart. It must be that there are streams of dust that are slowly forming themselves into comets. Getting it exactly backwards. Brilliant science. Almost correct. But almost correct in a wonderful way, because he's not afraid to push the data, to push the idea to the breaking point and, let's face it, beyond the breaking point. My own experience in this sort of being, so clever you're wrong, I was reminded of a few years ago when I was reading Harry Potter. I love science fiction. The moons of Saturn are not covered with mice. They're covered with ice. And I'm sitting there reading that and going, that was my master's thesis! Back in the days when I was at MIT, I had to write a thesis about the icy moons of Jupiter and what they were made out of and how they were put together and how the surfaces would be covered with ice and the rocky parts would be in the center. And I could even tell you how much of them were ice and how much were rocky by looking at the density of the moon and knowing the density of rock and then knowing the density of ice. You can calculate what were the proportions that give you the density. And I was doing this all starting about 1973. The first spacecraft didn't actually get to Jupiter until 1975. How did I know that the moons were covered with ice? How did I know that there was a lot of ice in those moons? About 10 years ago, I was invited to be one of the authors on the lead chapter of the University of Arizona's Space Science series of books, each book a collection of scholarly treatises on a particular topic. This book was Europa, the iciest moon of, certainly the iciest covered moon of Jupiter. And I'm thinking, they're finally remembering my master's thesis. They're finally inviting me to be, the chapter that I was going to be a part of was the history chapter. Because everything I did pre-spacecraft is historical, and that's about it. So I described my little master's thesis and how Jupiter was put together and how Europa was put together. And I thought, well, if I'm writing a history chapter, here I am at the Vatican Observatory. My office is in the gardens surrounding the Pope's summer home in Castel Gandolfo. Beautiful setting. And we've got a lovely library because when we moved out there in the 1930s, the Vatican libraries decided to clear house by dumping on us all of their modern science books. To them, modern means printed with a printing press. So we've got the complete collection of the philosophical transactions of the Royal Society going back to 1665, and books going back to the 15th century. And certainly astronomical books from the 18th and 19th centuries. And it occurred to me to ask the question, who was the first scientist to recognize that Jupiter's moons were made of ice? I knew it before the spacecraft were there. I was taught this by my professors even before we had spectra, which are in the infrared, that show that ice is there. You can't tell from the visible, you have to look in the infrared. Infrared detectors are pretty modern. When did people know that? Well, what do you need to know? What did I use to know that they were made of ice? First is the density. Now, you understand how the density is going to tell you what the composition of the inside is. Density. Density is the amount of stuff divided by the volume that the stuff is packed in. Bigger number, denser stuff. Every kid knows what density is. I remember when I was a kid growing up at Christmas time, we were allowed to open one package before going off to church. And you wanted to make sure it was a good package, and you didn't want to waste your one package on a box of socks. So, you pick the box that had the best density. And that might be chocolate, or that might be a book, or that might be something wonderful. Density tells you what's inside the box, even if you can't open the box. How do you measure the density of a moon? Well, you've got to know its mass, and you've got to know its volume. Finding the mass of a satellite is really tricky because the satellite goes around Jupiter, and by how fast it's going around Jupiter, you can tell how massive Jupiter is, but every moon in a given orbit is going to go at the same speed, whether it's low mass or high mass. However, there are 4 big moons going around Jupiter, and you can watch how they perturb each other. Because as we heard in the previous lecture, every bit of mass pulls in every other bit of mass. Now that's going to take some pretty highfalutin mathematics. More than I can do. Fortunately, I don't have to do it because a guy named Laplace did it in 1803. And he came up with the masses relative to the constant big G, which was measured in 1795 by Cavendish. So by 1803, they knew the masses of the moons. And if you compare the numbers he published to the modern numbers, most of them are pretty darn good. His mass for Callisto is about 25% off, but all the others are within 10%. Pretty astonishing. How do you measure the volume of these moons? In a telescope, they're only a little dot of light. You can't actually see how big across they are. But they cross in front of each other, and their shadows cross each other. And you can measure how long it takes for a shadow to cause a moon to blunk out and then come back. And by measuring these mutual events, you can come up with a physical size, how big each of the moons were. And so I looked up in our literature and found that people had done this by about 1840. There's another clue that tells me that these moons are covered in ice. And that's how bright they are. If you're out in space reflecting sunlight back into an Earth telescope, for a given distance away, the amount of light you get can either be because you're big and dark or small and bright. By knowing the size and knowing how bright the object is, I can tell whether it's dark or bright. Well, these sorts of measurements were just the kind of thing that 19th century astronomers like to do. So I look up, did they know the albedo is the word we use, the brightness of the surface of the moons of Jupiter? Not only did they know it, but they reported that the brightness of the moons of Jupiter vary by a factor of 2, wildly and unpredictably. And I'm going, they do? I've looked at these all my life. They don't do that. What are you talking about? But it's in every book. The brightness. Not only that, but they figured out, oh, well, if they're changing brightness, it must be that they're a really funny shape, like a pancake. And sometimes you see the pancake face on, and that makes them bright. And sometimes you see the pancake edge on, and that makes them dim. Why would they be shaped like a pancake? Well, maybe they're spinning really, 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 really fast, and they get squished down that way.